Thank you so much for the intro, and thank you all for coming this early in the morning. I hope you're going to have a good time. So my name is Romain, this is Jiang, and we're excited to present our paper. We did this in collab with our advisor, Pedro Lopes at the University of Chicago. So, it is no surprise that today AI has taken the world by storm. The issue is like with all these systems, unfortunately, they all rely on something in common. They actually are symbolic, meaning that they reason with text. So for instance, if I want to solve an equation, I can use an LLM like ChatGPT, and it would do it wonderfully. And that AI is taking my input as text, did some reasoning through text, and outputs it back into text. While symbols are powerful, it's not the only way we interact with the world. So what if the problem was this?
Help me open this.
The solution could be pushed down very hard on the cap and twisted. But what does that mean? What does hard mean? This is where symbolic AI kind of breaks down, and it's hard to convey the correct knowledge to the user. We're not interested in text-based AI. Instead, we ask our question, what new form should these AI systems take? In other words, what if these AI systems were not symbolic, but embodied? And by embodied, I mean things that you can feel through your body, such as touch, force. So we envision a new form of AI that uses your body as an input by reasoning with non-verbal information and outputs it back into your body. So let's take a look at our system in action. So here we have a user that is cycling. They're wearing a suit with electrical muscle stimulation. I'm assuming everyone knows what it is, but basically you're sending a small electrical pulse and that causes an involuntary muscle contraction. In addition, the suit has IMU, inertial measurement units, to track the full body pose. She's wearing a smart glass that has a camera to capture what she sees and a microphone to listen to her commands. As she walked up to the bus, she noticed an unfamiliar bike rack. So she prompts the system.
EMS, help me with this bike rack.
The system takes a picture through the smart glass, and in conjunction with what she said, it kind of take the information and reason through it. Before doing anything, the system indicates,
I'm going to move your right arm and hand.
So which limbs are about to move? The user confirms.
EMS, continue.
And as the user confirms, the system moves the user to reach for the handle. So every time you see a lightning bolt, that's an involuntary movement caused by the muscle stimulation. So this is This is actually a training facility in Chicago to help people practice. This is because this task is so physical that watching a video or reading instructions about it, it's actually not enough to help people put their bike on the rack. And we achieved this system through a Multimodal-AI architecture shown here. And we also open source the code, so if you guys want to try, you can go to that link. So I want to move on to a live demo. So let's give it a try. So here, I'm wearing a smart glass that has a camera and a microphone. Go to the screen. Move your cursor right there. No. There we go. Cool. So let's say I need help using this item, a spray can. Cool. So I'm going to prompt the system, EMS, help me. Capture. Cool. So here, it actually captures the contextual clues, and it found that this is a spray can, likely to be of paint, which is true. So we actually distill this information, this is through our AI system, into their descriptive all the way down to into muscle stimulation. So you can see here are much more verbal muscle instructions through commands. So we'll just run through the actual instructions. So let's give it a shot. Okay. So it's telling me that I should probably shake the spray can. Let's keep going. So you see here there are other instructions. Those are shoulder, but here I don't have any electrodes on the shoulder, so it's just going to skip it. Let's keep going. So here it actually tells me to press down on the nozzle. So this is true. It's actually telling me to shake the spray can and then press it for painting. Let's move on to another scenario where instead of spray painting, we are maybe like in the kitchen, maybe cooking. So let's try it again. EMS, help me. Awesome. So now the description is very different. Here it says cooking pot, it has some kitchen element. This is because it recognizes this is part of a kitchen appliance. So if we go all the way down to the muscle instructions, let's run through all the instructions. So it's actually telling me to press down the nozzle. And this is true because a cooking oil does not need to be shaken, it just needs to be pressed. So it is using contextual clues in order to create the muscle instructions. All right, so this is only possible because in addition to contextual clues, it understands and adapts. For instance, here we take the pose, a picture, a text, and even geolocation. For instance, Germany, we have very fancy windows. And all this into one single system, our system.
But even if with all these contextual clues, no AI is perfect in predicting the user and understand them. So we ran a user study to measure how people understand the generative muscle instructions in the ideal condition, like this one, with the correct instruction, but also, more importantly, with the injective wrong instructions to try to understand how they recover from errors. So the tasks include: take the pig out of the avocado, open the travel lock pill bottle, paint with a spray can, use an analog camera, move the nail with a nail sweeper, and open this unfamiliar window. Our study used pre-cached muscle stimulation instructions from our system, and the system did not read out the instruction beforehand. We went directly into the actuating movements. Now let me share some participants' reactions. For instance, here we see that even though muscle stimulation is not spatially precise, still she could understand the muscle instructions.
Oh, okay, like moving it closer, and then I pull it up.
To complete the task. And in the cases that we purposely inject wrong gestures, like this example here, look at her hand. The system is shaking the hand that does not have a spray can. Now let's see how she reacts to this erroneous movement. So she noticed the error and found her way around it.
Oh, it's doing it on this can. Okay. So I need to shake the can.
Or if all failed, we found that participants rapidly reprompted the system to generate new instructions and keep exploring. To wrap up, we're going to share some takeaways and future directions. We engineer an embodied AI system that assists users with electrical muscle stimulation. But unlike prior muscle stimulation systems that require one dedicated program for each different interaction, instead, our system adapts itself based on the context. Like here, it generates a shake gesture only when the user is using paint, but not for cooking oil. The flexibility in our system can allow researchers to generate muscle instructions movements for tasks that has never been explored in this type of haptic assistant before. Although we have this excitement, our work as the first paper that demonstrates a more embodied form of AI inherits the ethical concerns from both AI and physical assistance. We therefore design our system to let the user control it with commands such as EMS stop, and we wait for a user confirmation. On the other hand, we see a booming AI assistant throughout the modality as well. They work through audio, visual, or even tangible outputs. But we're more interested in the physical assistance that outputs with users' own gestures. And this brings us to a very interesting question. What is the limitation of machine-induced gestures? And what is the boundary of symbols, such as text and visual-based assistance? We can potentially design better output modality for the AI assistants with the limitations in mind. Furthermore, we're not the only ones trying to make AI think in a nonverbal way. Robotic researchers have been trying to make robots smarter by building physical AI. Our work is similar, but instead of controlling the robot, we're making the user move or automates the body. Then we ask, what's the boundary of automation? What tasks can be externalized to a robot? And what's the value of embodiment? In fact, last year at CHI, we showed that after muscle stimulation demonstrates movement directly to the body, people learn even after they take off the electrodes. We therefore expect that body automation could actually lead to body learning. As the user gets muscle instructions to perform the task, they might be learning the object mechanism at the same time. For example, here,
Oh, I see.
this is a clip from our user study, where this participant discovered the mechanism of an analog camera. We hope this will inspire future work on the development and evaluation of embodied AI. Thank you. We're happy to take questions.